Okay, so now it's time to move on to the next speaker. I'm very pleased to introduce Slobodan Tanushevski. He is originally from Macedonia. I hope I'm correct in saying this. And he holds a PhD from the State University of New York at Binghamton, and she's currently working at the Fluminense Federal University in Niterói. And today he's going to talk about Frattini-injective pro-peak groups. So please, Slobodan, it's over to you.
Thank you. I would like to thank the organizers for the invitation. This is a joint work with Ilur Snopcha. So let L over K be an infinite Galois field extension. The Krull topology on the Galois group of L over K is defined by taking as a base of open neighborhoods of the identity the family of all Galois groups of L over F, where F varies through the finite Galois extensions of K contained in L. I have a picture here. Now the subgroups in N are all normal and are of finite index in the Galois group of L over K. A subset of the Galois group of L over K is open in the Krull topology if and only if it can be written as a union of cosets of subgroups in N. With respect to the Krull topology, the Galois group is a compact Hausdorff and totally disconnected topological group. And the Galois group of a field extension is, with respect to the Krull topology, is a compact Hausdorff and totally disconnected topological group. Such groups are called profinite groups. A compact Hausdorff and totally disconnected topological group is called a profinite group. Equivalently, one can show that the class of profinite groups coincides with the class of topological groups that can be obtained as inverse limits of inverse systems of finite groups. For the Galois group of L over K, we have we can obtain the Galois group of L over K as the inverse limit of the finite Galois groups of finite Galois field extensions F over K contained in the field L. Now let P be a prime. A pro-P group is a profinite group in which every open subgroup has index some power of P. Since profinite groups are compact, open subgroups necessarily have finite index. And so if the index of every open subgroup is some power of P, then we say that the profinite group is called a pro-P group. Equivalently, a pro-P group is an inverse limit of an inverse system of finite P groups. I wrote some examples here. The prototypical example of a pro-P group is the additive group of the ring of p-adic integers, ZP. The group of invertible n times n matrices with entries in ZP is a profinite group, but it's not a pro-P group, although it has finite index subgroups, which are pro-P groups. Every Galois group of a field extension is a profinite group, but also every profinite group is the Galois group of some Galois field extension. And I want to mention one more example that is important for this talk. Let K be a field and let Kp be the compositum of all finite Galois P extensions of K inside a fixed separable closure of K. Kp is called the maximal P extension of K. And the Galois group of Kp over K is a pro-P group, and it's called the maximal pro-P Galois group of K. Now, one important object in the study of pro-P groups is the Frattini subgroup. Let G be a pro-P group. The Frattini subgroup of G is defined to be the intersection of all maximal subgroups of G. And here by a maximal subgroup, I mean a closed maximal subgroup. Since propy groups are topological groups, I will tacitly assume that all subgroups under consideration are closed subgroups. Okay. Now, just like for finite P groups, a maximal subgroup of a propy group is always normal and it has index P. Propy group. I wrote here some basic properties of the Frattini subgroup. Let G be a propy group, H and K subgroups of G, and X a subset of G. Then have a nice description of the Frattini subgroup. It's the product of G to the P, which is the subgroup generated by P powers of elements of G, times the commutator subgroup. This product might not be closed, so we have to take closure. The bar represents closure, logical closure. If H is a subgroup of K, then the Frattini of H is a subgroup of the Frattini of K. Have monotonicity. And G is generated as a topological group by the set X, if and only if the images of the elements of X generate the quotient of G by its Frattini subgroup. Okay. Now, given a propy group G, dG denotes the minimal cardinality of a topological generating set for G. Now, I want to mention a few facts about Frattinis of finitely generated propy groups. Well, first of all, the product of G to the P and the commutator subgroup is closed. We don't have to take closure here if G is finitely generated. The Frattini subgroup is an open finitely generated subgroup of G. It's open, so it's a finite index in G, and if G is finitely generated, it will also be finitely generated. And one more fact, G mod, its Frattini subgroup is an elementary abelian P group. And so it can be considered as a vector space over Fp, the field with P elements. dG, the minimal number of generators of G, is the dimension of the quotient of G by its Frattini as a vector space over Fp. Okay, so here's the central concept. So we defined a propy group G to be Frattini-injective if the function that maps a finitely generated subgroup of G to its Frattini is injective. Again, propy group G is Frattini-injective if the function H maps to the Frattini of H is an injective function from the set of finitely generated subgroups of G into itself. Now, I will give you several examples, many examples of Frattini-injective propy groups, but for the beginning, I just want to mention a few examples so that you know that this is not a vacuous concept. Torsion-free abelian groups are Frattini-injective, and also free propy groups are Frattini-injective. Okay. Now, here are some basic properties that can easily be derived from the definition of Frattini-injectivity. Let G be a Frattini-injective propy group, then the following assertions hold. Every subgroup of G is Frattini-injective. This is obvious. Yeah? Every subgroup of a Frattini-injective group is Frattini-injective. G is torsion-free. Every Frattini-injective group is torsion-free. This is also obvious since if a propy group has an element, non-trivial element of finite order, then it has an element of order P. Now, take the cyclic group generated by such element. What is the Frattini? The Frattini is the trivial group, but the trivial group is also the Frattini of the trivial group. Okay, So every Frattini-injective propy group is necessarily torsion-free. Okay. More interesting property, if x to the alpha equals y to the alpha for some x and y elements in G, and alpha periodic integer different than 0, then x is equal to y. Frattini-injective groups have the unique extractions, the unique extraction of roots property. And I would like to prove this for you. You see, it suffices to prove that if x to the p equals y to the p, then x equals y. So suppose that x to the p equals y to the p. Okay. Now we have that the cyclic or procyclic subgroup generated by x is equal to the procyclic subgroup generated by y. Okay. But you see, this here is exactly the Frattini of the cyclic subgroup generated by x. And here we have the Frattini of the procyclic subgroup generated by y. And now by Frattini-injectivity, we get that the cyclic subgroup generated by x is equal to the cyclic subgroup generated by y. And of course, since Frattini-injective groups are necessarily torsion-free, this cyclic subgroup is isomorphic to ZP. Okay. Now we have x and y belong to the same cyclic subgroup, right? And we have x to the p equals y to the p. By the unique extraction of roots property of ZP, we can now conclude that x equals y. Okay. Now the reason I showed you this this proof is because, you see, if you think about the proof, what I use in the proof is the fact that we have Frattini-injectivity on cyclic subgroups. The condition of Frattini-injectivity imposed only on cyclic subgroup is equivalent to the unique extraction of roots property. So we can think of Frattini-injectivity as a wide generalization of unique extraction of roots. And I wrote one more property. If H and K are subgroups of G, and H is a finite index in K, then DH is greater or equal than DK. The minimal number of generators for H is greater or equal than the minimal number of generators for K. Of course, this is interesting if K and H are finitely generated. So when you pass to a finite index subgroups, the minimal number of generators cannot decrease, can stay the same or increases. So this is a quite restrictive property on a propy group. Okay, I will postpone a bit more, showing you more examples, because you see there are obvious ways of sharpening the Frattini-injectivity condition. For example, we say that a propy group G is strongly Frattini-injective if the function that maps a subgroup H to its Frattini is injective. So G is Frattini-injective if the function H maps to its Frattini is if the function that takes a finitely generated subgroup to its Frattini is injective. We said it is strongly Frattini-injective if for every subgroup H, the function that, if for all subgroups, the function that takes H to Frattini of H is injective. Okay. Here is a more interesting idea. A propy group G is defined to be Frattini resistant if for all finitely generated subgroups H and K of G, if H is a subgroup of K, if and only if the Frattini of H is contained in the Frattini of K. Okay. Now, for every propy group G, we have that if H is contained in K, then the Frattini of H is contained in the Frattini of K. Here we require the converse. Okay, so if the Frattini of H is contained in the Frattini of K, then H is contained in K. So you see, but if you look at the set of finitely generated subgroup, that's a poset, it's a partially ordered set with respect to inclusion. And so the condition of Frattini resistant says that the map that takes a finitely generated subgroup to its Frattini should be an embedding of the poset of finitely generated subgroups into itself. And of course, since every embedding of posets is injective, follows that Frattini resistance implies Frattini-injectivity. If a group is Frattini resistant, then it's Frattini-injective. And of course, we have a strong form of Frattini resistance. Here we impose the condition of Frattini resistance on all subgroups of G. So here's why, first of all, here's why we chose the name Frattini resistance. So this proposition, a property group G is Frattini resistant if and only if for every finitely generated subgroup H of G and every X element of G, if X to the P belongs to the Frattini of H, then X belongs to H. So you see that the Frattini of H, this is the idea, the Frattini of H refuses to accept elements that do not belong to H. This is a quite the definition, the embedding of posets definition is quite abstract. And this is something much more concrete that one can work with. Now, for finitely generated property groups, we have the following equivalent statements. If G is strongly Frattini resistant, G is Frattini resistant. Strong Frattini resistance and Frattini resistance are the same for finitely generated property groups. And further, we can the condition for all open subgroups U and V of G. If the Frattini of U is contained in the Frattini of V, then U is contained in V. You only need to check the condition of Frattini resistance on open subgroups. And the other version, for every open subgroup U of G and every maximal subgroup M of U and every X element of U, if X to the P belongs to the Frattini of M, then X belongs to M. There are a lot of universal quantifiers here, but actually it's a nice condition one can work with. And you see, exactly because of this characterization, or the original one, this one, exactly for this reason, I said that Frattini-injectivity is somehow can be thought of as a generalization of unique extraction movements. Okay, now examples. The Mushkin groups, they are pro-P-Poincare duality groups of dimension 2. Don't worry if you don't know what that means. They appear they naturally appear in number theory, the Mushkin groups. If K is a p-adic number field containing a primitive p-root of unity and Kp, which is the maximal p extension of K, then the Galois group, the maximal pro-P Galois group of K is a Demushkin group. Furthermore, the pro-P completion of any orientable surface group is also a Demushkin group. Now I'll tell you what happens with Demushkin groups. Let G be a Demushkin group. All Demushkin groups are finitely generated, and set D to be the minimal number of generators for G. Then we have two possibilities. Either the abelianization of G is torsion free, or it has a finite cyclic factor. We have at most one finite cyclic factor. Now, if it's torsion-free, then we set Q to be equal to 0. And if it has a finite cyclic factor, then we set Q to be the size of this cyclic factor, the order. Let G be a Demushkin group, then the following assertions hold. If Q is different than P, or Q is equal to P and P is odd, then G is strongly Frattini resistant. If Q is equal to 2 and dG is greater than 2, then G is Frattini-injective, but not Frattini resistant. You see, it's not at all obvious that Frattini-injectivity and Frattini resistance are different conditions. This example here shows that they are actually different concepts. And in fact, I don't know of any other example of a Frattini-injective group that is not Frattini resistant. If Q is equal to D is equal to 2, then G is not Frattini-injective. This is what happens with the Demushkin groups. Now recall that for a given field K, we denote by Kp the maximum P extension of K. And the Galois group of Kp over K is the maximum pro-P Galois group of K. Now let P be an odd prime, and let K be a field that contains a primitive P root of unity. Then the maximum pro-P Galois group of K is a strongly Frattini resistant pro-P group. If P is equal to 2, then we should also assume that square root of -1 belongs to K. In that case, the maximum pro-P Galois group, the maximum pro-2 Galois group of K is a strongly Frattini resistant pro-2 group. Now, this was in fact this is one of the incentives for studying the concept, for trying to understand the concepts of Frattini-injectivity and Frattini resistance, because the problem of classifying maximal pro-P Galois groups over fields that contain a P root of unity is a well-known problem in abstract Galois theory, and a lot of progress has been made recently in understanding these groups. Most notably, it follows from the solution of the Bloch-Kato conjecture by Ross and Voevodsky that the cohomology algebra of such group is quadratic, which means that it's generated by elements of degree 1 and is defined by homogeneous relations of degree 2. Okay. This is a very deep result. So if the maximum pro-P Galois group over a field that contains a P root of unity, primitive P root of unity has this property that the cohomology algebra is quadratic. Okay. I also mentioned that the problem of classifying maximal pro-P Galois groups over fields that contain a primitive P root of unity is of course difficult, but it doesn't seem impossible. So there is a conjecture by Ido Efrat that gives, at least for the finitely generated groups, it gives a very nice, pleasant description. Now I want to turn to p-adic analytic pro-P groups. A pro-P group is called p-adic analytic if it has a structure of an analytic manifold over QP, with respect to which the group operation are given by analytic functions. So if it's a Lie group over QP, QP here represents the field of p-adic numbers. Here are some examples. Gamma I represents the kernel of the homomorphism from GLNZP to GLNZP mod PIZP, homomorphism induced by the homomorphism, by the ring homomorphism. Then gamma I is a periodic analytic pro-P group for each I greater or equal than 1. And in fact, every periodic analytic pro-P group is isomorphic to a closed subgroup of GLNZP for some n. So here's what happens with Frattini-injective periodic analytic pro-P groups. We were able to classify the Frattini-injective periodic analytic pro-P groups. Let G be a periodic analytic pro-P group. The following statements are equivalent. G is Frattini-injective. G is Frattini-resistant. Here it's the same thing. G is isomorphic to one of the following groups. It's either torsion-free abelian, or is a special type of semidirect product. Here, the generator X of the cyclic factor acts in a very simple way. Scalar multiplication by lambda, with lambda equal to 1 plus p to the s for some s greater or equal than 1 if p is greater than 2 if it's an odd prime, and lambda equal to 1 plus 2 to the s for some s greater or equal than 2 if p is equal to 2. Okay. Now let's move to solvable pro-P groups. Here's what happens with solvable pro-P groups. Let G be a solvable pro-P group. The following statements are equivalent. Again, G is Frattini-injective, G is strongly Frattini-resistant. G is a free abelian or isomorphic to the same type of semidirect product, with the only difference that now the abelian group can be infinite rank. Okay, but we have the same type of action. So you see, the periodic analytic groups are all meta-abelian, and we don't get any new solvable pro-P groups that are Frattini-injective. And now, as a consequence of these two theorems, we get a classification of maximal pro-P Galois groups over fields that contain a primitive p-root of unity and which are solvable periodic analytic. Let G be a solvable periodic analytic pro-P group. Then G is Frattini-injective if and only if it is isomorphic to the maximal pro-P Galois group of K for some field K that contains a primitive p-root of unity and also contains square root of -1 if p is equal to 2. Okay. Now, the classification of such maximal pro-P Galois groups of periodic analytic and solvable maximal pro-P groups is not new. That's already known. In fact, War classified maximal pro-P Galois groups or fields that contain a primitive p-root of unity. Now, actually, for fields that contain a primitive p-squared root of unity. And then Quadrelli extended this result to all groups, to all fields that contain a p-root of unity. However, their proofs use deep results on Galois theory. See, for example, Var uses the Merkurjev-Suslin theorem, which is a special case of the Bloch-Kato conjecture. Bloch-Kato conjecture establishes a connection between Milnor-K theory and Galois cohomology. Quadrelli uses the full power of the Bloch-Kato conjecture. He uses the fact that the cohomology algebra is quadratic. Now here we have derivation of this classification result. We have proof of this classification result that doesn't use any deep results. It's based on elementary group theory. Elementary in the sense that we don't use anything more than standard result on periodic analytic groups and solvable pro-P groups. Okay. In particular, there are no cohomological arguments in this proof. The lattice of normal abelian subgroups. Let G be a Frattini-injective Pro-P group, then G has a unique maximal normal abelian subgroup N. I don't know if this is clear, but I'm looking at all normal abelian subgroups. There is one that is largest. Moreover, the following assertions hold. N is isolated in G, which means that if X to the P belongs to N, then X belongs to N, has this property. Every subgroup of N is normal in G. We have a full description of the lattice of normal abelian subgroups. It's simple. If the center of G is non-trivial, then N is equal to the center. And if the center is trivial, but N is not trivial, then G splits as a semi-direct product, CP semi-direct product, the centralizer of N in G, and the center of the centralizer is N. Now, again, for maximal Pro-P Galois groups or fields that contain a primitive p root of unity, the existence of a unique maximal normal abelian subgroup is known, has been known, and it's a theorem of Engler and Nogueira and another paper of Engler and Koningsman. Should be finishing. But I want to mention one thing. Here, we actually believe that G should split as a semi-direct product over N. We're quite close to proving this, but somehow it escapes us. But we conjecture that G actually splits as a semi-direct product over N. So if the group has a non-trivial center, then we have a splitting as a direct product, the center times something else. Okay, I think I will stop here.
Okay, yeah, so let's thanks a lot, Slobodan, for this very interesting talk. So just a quick round of applause for him.